Okay, good morning. This is Professor David J. De Los Reyes. Okay, I will be discussing tonight or this morning. This is circuit lesson number 16. Okay, let's proceed. Subject matter for this morning. This is circuit lesson number 16, and the title of the topic is Superposition Theorem Example Problem. The last time around, I have discussed the concept on how to compute for the current any part of the circuit if we try to solve the problem considering superposition theorem. So, for this morning, I will be giving you an example problem to illustrate that superposition theorem. Okay, the problem is this one. We've got a given figure. It's just a simple one. We got a circuit which comprises two voltage sources, 24 volts and 12 volts. And the resistances included are actually 4 ohm, 6 ohm, and 12 ohm. To illustrate the concept of superposition theorem, the problem is asking what will be I, so 12 ohm equal to. With this configuration, what will be the total current passing through the 12 ohm load? Okay, let's try to bring out the solution of this one by using superposition theorem. If we try to bring out the solution, we'll consider first the 24 volt source. Then we short out the 12 volt source. So it seems this is non-existent. Okay? So the configuration will be something like this. It's the same as the original, except that the 12 volt source is gone. I think that was the first step on the concept of the solution of the superposition theorem. Consider one voltage source, okay, then try to short out the other voltage source. So if we try to consider the 12 volt source, we shorted out the 12 volts, so it seems that 12 volt is gone. Okay, and by using our knowledge of the so-called series parallel concept, we could compute for the current passing through this 12 ohm due to the 24 volt source. And to do that, we must have to simplify first the resistances. We must have to compute for the total single equivalent resistance of the circuit if we try to neglect the 12 volt source for the meantime. So the 12 volt source is neglected. Okay, so this 12 ohm, this is 6 ohm. They are in parallel. Okay, and the single equivalent of this one will be in series with this one. So actually we are using the concept of series parallel combination. So I place it here, RE1 will be the product of 6 times 12 all over the sum. This is actually the formula on how to compute for the single equivalent of this one. There are only two, so it will be the product all over the sum. So this is 6 times 12 over 6 plus 12. And that will be 72. This is 12, right? Over 18. And that is 4 ohms. So the single equivalent of this one will be 4 ohms. Okay? And to compute now for the total resistance, considering the 24 volt source, this 4 ohm will now be in series with this one. So instead of specifying the designation RE2, actually that will now be our total resistance considering the 12 volt source. So capital letter R with the subscript T1 should be equal to 4 plus 4. This 4 here will be in series with the single equivalent of this one, so it will come out to be 8 ohms. Right? And if the single equivalent resistance now will be equal to 8 ohms, it seems we got the voltage source here. This is 8 ohms and this is 24 volts. So actually we could compute for the total current, right? We are given a single equivalent resistance connected to a 24 volt source. So by using the equation voltage equal to IR, I now will be equal to B over R. Okay, so it will be 24 over 8 and that will be 3 amperes. So meaning to say, for this, the total current coming from the 24 volt source without the 12 volt will be 3 amperes. And by using our knowledge of the so-called Kirchhoff's voltage law, this will be the resulting equation. Okay? If we try to take the summation of the voltages across this 12 volts here, 24 volts, minus the voltage drop here, minus the voltage drop here, should be equal to 0. Or if we compute for the voltage across this, it should be 24 minus the voltage drop on the 4 ohm load. So I place it here. Voltage across the 12 ohm load will be equal to the total applied voltage minus the voltage drop on the 4 ohm load. Okay, the total current passing through this is 3 actually. So this will be the difference of 24 minus 12, and what will come out will be 12 volts. The main reason why we compute for the voltage across this, because if we know the voltage across the 12 ohm load, again by using the equation voltage equal to IR, I will be the ratio voltage over R. Okay, so considering the voltage current passing to the 12 ohm load, its voltage across it is actually 12 volts, and its total resistance is actually 12 ohms. So 12 volts over 12 ohms is actually 1 ampere, and the direction is downward. It is this. It's downward. Due to the 24 volt source, the current passing through the 12 ohm will be 1 ampere. Okay? Superposition, right? We consider the first voltage source already, so we will consider again the next voltage source. We shorted out the first one. So if we try to consider the 12 volt source, this was originally, I'll bring it back. This is 12 volts, right? We consider this one already, so we will consider next one, the 12 volt source. So we will short out the 24 volts, so it seems that 24 volt is non-existent. So what will come out will be this figure here. Right? This is 4 ohm. This is the location of the 24 volt source. It's non-existent for the meantime. 6 ohm. This is 12 ohm. This is 12 volts. Again, by using our knowledge of the concept of series parallel, we shall compute for the voltage across this. Because upon solving the voltage across this, by taking the ratio voltage across this over 12, we could compute for the current passing here. But to do that, we must have to simplify for the circuit. These two here is actually in parallel. So if I will try to take the single equivalent, it will be the product over the sum. 4 times 12 over 4 times 12, this is 48 over 16. And luckily 48 over 16 is 3. So the single equivalent of this 4 and 12 will be equal to 3 ohm. Okay? This 3 ohm here will now be in series with the 6 ohm. So I place it here, capital letter R with the subscript T2 will be equal to 3 plus 6. So 3 plus 6, that will be equal to 9 ohms. So meaning to say, we are given the circuit again. This is 12 volts and this is 9 ohms. So we could compute for the total current again by using the equation voltage equal to IR. So current will be voltage over resistance. So this will be 12 over 9 and that will be 1.34 amperes. So the total current coming from the 12 volt source, okay, when the 24 volt source is neglected, it is, where is it? 1.34 amperes. Right? And if we try to take the summation of the voltages across the right loop, the 12 volt source minus the voltage drop here minus the voltage drop here should be equal to 0. So if we try to compute for the voltage drop here, it should be the applied voltage minus the voltage drop on the 6 ohm load. Right? So it's the same as the first one. We take the summation of the Kirchhoff's voltage law, meaning 12 volt minus the drop here minus the drop here should be equal to 0. If we try to compute for this, it will be 12 minus the drop here. So this will be 12. The drop across the 6 ohm load is actually its current passing times 6. So this is 1.34 times 6. 12 minus, this is approximately 8. Okay. So the voltage across the 12 ohm load will be 4 volts. The voltage across this will be equal to 4 volts. Right? So if we know the voltage, we know the resistance, we compute for the current. So this will be the ratio 4 over 12, and that's 1/3 or 0.34 amperes. The direction is still downward. It is this. Right? And according to the so-called superposition theorem, okay, the voltage across any part of the circuit will be the value of the superimposed current when all the voltage sources are actually considered. So, capital letter I with the subscript 12 ohm, okay, will be equal to total now. Okay, by bringing out superposition theorem, it will be the summation of the superimposed current considering one voltage source at a time. So, considering the 24 volt source, that's 1 ampere. Considering the 12 volt source, it's 0.24 amperes. So, this is 0.34. Okay, in accordance to superposition theorem, we use that one. The total current passing through the 12 ohm load will be equal to 1.34 amperes. Okay, as simple as that one. That's superposition theorem. The current passing here will be the current given by the first voltage source plus the current given by the second voltage source. Okay, and since the direction are actually the same, we will just add the magnitude. Okay, that will be our magnitude, and we will indicate that the direction of the current will be downward. Okay, good morning from Los Angeles. Professor David de los Reyes, an example problem of a superposition theorem.